Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the regenerative Brayton cycle. In gas turbine engines, the temperature of the exhaust gas leaving the turbine is often considerably higher than the temperature of the air leaving the compressor. Therefore, the high-pressure air leaving the compressor can be heated by transferring heat to it from the hot exhaust gases in a counterflow heat exchanger, which is also known as a regenerator or a recuperator. A sketch of the gas turbine engine utilizing a regenerator and the TS diagram of the new cycle are shown in figures 1031 and 1032 respectively. The thermal efficiency of the Brayton cycle increases as a result of regeneration, since the portion of the energy of the exhaust gases that is normally rejected to the surroundings is now used to preheat the air entering the combustion chamber. This, in turn, decreases the heat input requirements for the same network output. Note, however, that the use of a regenerator is recommended only when the turbine exhaust temperature is higher than the compressor exit temperature. Otherwise, heat will flow in the reverse direction, decreasing the efficiency. This situation is encountered in gas turbine engines operating at very high pressure ratios. Firstly, let's talk about the regeneration effectiveness when a regenerator can be reasonably used. In order to measure the utilization of the waste heat of the high temperature exhaust gas in the regenerator, the regeneration effectiveness F is defined as the ratio of the heat absorbed by the air in the regenerator to the maximum heat that the exhaust gas may give off in the regenerator. The state temperature of gas leaving the gas turbine, T4, ideally can be reduced to the air temperature leaving the compressor, T2, in the regenerator. For the zero regeneration effectiveness, there is no regeneration. For the unity regeneration effectiveness, this is an ideal regenerative Brayton cycle, and we have T4 equals T5 and T2 equals T6. The effectiveness of most regenerators used in practice is below 0.85. With the definition of effectiveness, the temperature of the air leaving the regenerator is the temperature of the exhaust gases leaving the regenerator is. Secondly, let's try to evaluate the heat efficiency for the gas turbine engine with regenerator. By definition, the heat addition and the heat rejection are. By definition, the thermal efficiency can be expressed as, based on the process, the temperatures for the three states are substituting and simplifying yield with unity effectiveness and under the cold air standard assumptions. The thermal efficiency of an ideal Brayton cycle with regeneration is expressed by equation 1060. Okay, that's all for this task. Thank you very much and see you next time.